Bismillah ar-Rahman ar-Rahim. Assalamu alaikum and very good morning. This is Group 3. We are presenting XRD simulation. This is the member of Group 3. We have Ibtihar Rashid, Muhammad Abdul Munim, and Nur Yuni. So without further ado, let's start with the introduction.
XRD stands for X-ray diffraction. It is an analytical technique used to study crystalline materials. When X-rays hit a material, they interact with the crystal structure and produce diffraction pattern. This pattern helps identify the material and understand its crystal structures. The basic principle of XRD is based on the reflection of X-ray from crystal planes. When X-ray strike the crystal at specific angle, constructive interference occurs. This interference creates peaks in the XRD pattern, which provide information about the crystal structure. Bragg's law explains the condition for X-ray diffraction. The equation is n lambda equal to 2d sine theta, where lambda is the X-ray wavelength, d is the distance between the crystal and the planes, and theta is the diffraction angle. This law explains why diffraction peaks appear at certain angles in an XRD pattern. XRD has some limitation. It can be used to identify crystalline phases, determine crystal structure, and estimate crystalline size. However, XRD cannot determine particle shape, full particle size, or chemical composition alone.
This is the overview of the website simulation. First, we select the specimen to be analyzed. In this demonstration, a silicon powder sample is chosen because powder sample contain randomly oriented crystal producing clear diffraction peaks. After selecting, the door option will unlock automatically. The instrument status panel shows that the X-ray shutter is closed, ensuring safe condition before starting the scan. Next, the X-ray tube is switched on. The voltage and current control the intensity of the X-ray beam. The scan range is set from 10 degrees for the start angle and 80 degrees for the end angle, which allow us to capture most diffraction peaks of crystalline material. A step size of 0.02 degree is used to achieve good resolution while keeping the scan time reasonable. The scan rate controls how long the detector collects data at each angle. A moderate scan rate improves signal quality, set at 0.08 degree per second. Based on the selected parameters, the simulator automatically calculates the total scan time. Once the scan begins, the diffraction is generated. Each peak corresponds to diffraction from specific crystal plane. The peak width, also known as the full width at half maximum, will later be used to estimate crystalline size. The diffraction pattern is safe for further analysis using Bragg's law. Here we choose one prominent diffraction peak located at approximately 30 degrees in 2 theta.
So now after we get our simulation out of the way, we will try to calculate the d distance in the crystal. And for that, we're going to use Bragg's law. As we stated earlier, Bragg's law is n times lambda equal 2d sine theta. So the assumption are the n in the level 1, which is order 1 of the reflection, and the lambda will be the X-ray wavelength, which is 1.54 angstrom meter, which is typically the wavelength for Cooper source. And for the calculation, we need to find the theta first. So 2 theta equal 30 as we get it from the simulation. So the theta will equal 15. So we rearrange the formula. It will become d equal lambda over 2 sine theta. After that, we just substitute the value and then we get the answer d equals 2.97 Armstrong meter. Okay, so second we will use the Sechler equation, which is relate the full width at half maximum of peaks to the size of the crystal grain. So the formula as follow: tau, which is the size of crystal grain, equal k, the shape factor, multiply lambda, wavelength, over beta, which is full width at half maximum, multiply cosine theta. So for constant, the k is constant, we'll use 0.9, and the beta from our result, for a high resolution result like ours, we can assume it's equal 0.1 or 0.2. In this case, it's 0.1 degree. So for the calculation, first we need to convert beta from degrees to radian. So 0.1 multiply by over 180, we'll get 0.00175 radian. After that, we substitute all the value in the formula, and we use the theta, same like the previous, 15. So we'll get the value tau equal 819.9 Armstrong, or 81.99 nanometer. So in conclusion, this project demonstrates the use of the MyScope XRD simulation to analyze material crystal structure by applying Bragg's law to the simulated peak at 2 theta equal 30 degrees. We successfully calculated D spacing of 2.976 Armstrong meter. Furthermore, using the Sachar equation with an observed full width at half maximum of 0.1 degree, we estimated a crystallinity size of approximately 81.99 nanometer. This result highlights how XRD serves as a critical tool for phase identification and structural understanding, while also acknowledging that its effectiveness is limited to crystalline structures and does not measure individual particle morphology. Okay, that's all from our group. Thank you for listening.